Ma'am, make me the host, ma'am. Good evening, everybody.
Good evening, sir.
Yeah, make me the host, ma'am.
Yeah, sir, I did it.
Yeah, thank you. Sometimes my camera works, huh? All right, shall we continue, students?
Yes, sir. Good evening, sir.
Good evening to all.
Good evening, sir.
Yeah. We will learn the next set of problems today and the last part of the topic. Tomorrow, possibly, we will finish up with this chapter. Okay, so tomorrow I'll have to talk about the different types of crystal defects. We'll learn that possibly today along with some of the numericals. And tomorrow, maximum, we'll try to finish up with this chapter. Let's see. Now, we have to rush. Now, the ionic radii of A plus and B minus are 0.89. A plus is a cation. Positive charged ions are called as cation. And they have given the radius, ionic radius, as 0.98 into 10 to the power minus 10 meters. And for B minus, it's an anion. Negative ion will be called as anion. And they've given the radii as 1.81 into 10 to the power minus 10 meters. They're asking you to calculate the coordination number. Coordination number. I told you coordination number is number of atoms are bonded or related to the atom which is under reference is called as coordination number. We learned in case of what a cesium fluoride, cesium chloride, I drew a structure like this. Cesium is at the center and chlorine atoms are at the corners, 8 corners of the cube. That means this cesium is linked to 8 chloride. Therefore, the coordination number of cesium is 8. That is what we learned. And number of elements or atoms surrounding an atom which is under reference is called as the coordination number. In order to find the coordination number, we need to know something called as radius ratio. Radius ratio is given by the formula radius of cation to radius of anion. That is nothing but radius of A plus by radius of B minus. So it is 0.98 into 10 to the power minus 10 meters divided by 1.81 into 10 to the power minus 10 meters. On simplification, you will get this to be 0.541 meter. You will get the the answer you'll get it as 0.541. This 0.541 is the radius ratio. Now, if you remember, 0.541 is the radius ratio. It is in the option D, because in the previous radius ratio chart, if you observe, you can know that. I told you to remember the chart, radius ratio. See, 0.541 is in between 0.414 and 0.732. That means the coordination number is 6 and it will have an octahedral geometry. Okay, so the question is, what is the question they've asked? We'll see. The question what they've asked is, what is the coordination number? Since the radius ratio lies between 0.414 and 0.732, the coordination number will be 6. Therefore, the answer for this question is option D. See, this radius ratio chart is very important. So predicting the structure based on radius ratio, you can learn only if you know the chart. Kindly remember. Did you understand this?
Yes, sir.
Yes. The next question. In calcium fluoride, having fluorite structure, calcium fluoride has fluorite structure. Do not get confused to cesium chloride. Calcium is different, cesium is different. Okay, they have different structures. See, calcium fluoride has fluoride structure. The coordination number of calcium ion and fluoride ion, this Geometry, if I have to draw or if I have to picturize it, it is complex. So kindly remember the structure. Remember this answer. For calcium fluoride having fluoride structure, the coordination number of calcium is 8 and of that fluoride is 4. Therefore, the answer for this question will be option C, 8 and 4. The structure looks complex. I didn't have time to download and put the picture. I actually forgot, not time, I actually forgot. So anyways, now you remember in calcium fluoride having fluoride structure, the coordination number of calcium and the fluoride ions are 8 and 4. 8 and 4. The next question. A metal crystallizes out with a cubic structure having edge length 361 picometers. 361 picometers. There are 4 metal atoms in one cell. What is the radius of one atom? See, the question is little tricky. It is not a complex question, it's a tricky question. A given metal crystallizes out in a cubic structure having edge length 361 picometer. If there are 4 metal atoms in one cell, what is the radius of one atom? Can you tell me what is the understanding? They have given you edge length. They have given you edge length to be 361 picometers. What else is given? Can anyone tell me what else is given? What else is given? Read the question. A given metal crystallizes out in cubic structure having edge length 361 picometer. If there are 4 metal atoms in one cell, 4 metal atoms in one cell, what is the information you get, students? Any information? Anything? Participate. There's nothing wrong in giving the, no, if the answer is wrong. You tell me what you're understanding. I just want to know what you're getting at. Ritika, yeah, tell me. Dhanalakshmi, Rupashri, Ajay.
Particles is equal to 4.
What is equal to 4?
Number of particles.
4 particles. What does it mean?
FCC.
Very good. That means Z is 4. It means it has what cubic structure? It has a face center cubic structure. See, they have not given you the face center directly. In order to confuse, they have said if there are 4 metal atoms in one cell, so face center cubic lattice will have what? 4 atoms. We have done this problem. So therefore, the structure of this metal is what? FCC. Now, once you understand that this is FCC, how do you, how does that atomic radius related to radius related to the edge length? We know that R is equal to root 2a by 4. Root 2a by 4. So root 2a they've given, edge length they've given 361 divided by 4. On simplification, you will get 127 picometers. The answer what you will get is 127 picometers. Hence, the answer for this question is option B. Good. Did you understand this? Did you understand this question? Yes. The next question is, where's that? Yeah, cursor. See, cesium bromide. Cesium bromide crystallizes in body-centered cubic lattice. Cesium bromide crystallizes in body-centered cubic lattice. The unit cell length is 436 into 10 to the power, 436. That means they've given you A to be 436.6 picometers. So it'll be, how many meters it'll be? 436.6 into 10 to the power minus 10 meters. See, picometers is 10 to the power minus 12. If you have to convert it into meters, it will be 436.6 into 10 to the power minus 10 meter. Since they say cesium bromide crystallizes in BCC, Z will be what? 2. Z will be 2. They have given the atomic mass of cesium to be 133 units and bromine to be 80. So therefore, what will be the molecular mass of cesium bromide? It will be 133 plus 80. 133 plus 80, it will be equal to 213. It will be 213. This will be the mass. Now they're asking you to calculate what is the density of cesium bromide. We know the density is given by the formula Z into M divided by A cube into Na. Z we know it is 2. Molecular mass we found out is 213 now. All right. And A is what? 436.6 into 10 to the power minus 10 the whole cube. 436.6 into 10 to the power minus 10 the whole cube. And Avogadro's number it is 6.02 to 10 to the power 23. So this is mathematics. If you can simplify, this is a simple mathematics. If you simplify the value, what you will get for density is 8.50 gram per centimeter cube. 8.50 gram per centimeter cube. So there is a conclusion here. The density is 8.50 gram per centimeter cube. For a unit cell, the density will be, for a unit cell, density will be 8.50 by 2, because each particle has contribution is how much? 2. BCC contribution is 2. Therefore, divide by 2, you will get the density to be 4.25 gram per centimeter cube. Hence, the answer for this question is option D. The answer for this question is option D. Followed with this?
Yes, sir.
Yeah. Few more questions, 1 or 2 more questions, and then we will start with the topic today. Edge length of a cube is 400 picometers. Edge length of a cube is 400 picometers. That is, A is 400 picometers. Its body diagonal in picometers would be, they've given the options in picometers. Therefore, they're asking nothing to change. You can use body diagonal. What will be body diagonal? Hence, body diagonal would be, what is that body diagonal? Now, if you can remember this chart, what I told, what I gave you here. Oh, no. Body diagonal, not this. Okay. So I think I worked out the derivation. Those derivation I have not saved that. In the derivations, it will be body diagonal. All right. So I'll give you the formula and then we'll work out. The body diagonal will be square root of 3 into A. Edge length of a cube is 400 picometers. Its body diagonal will be, body diagonal is given by square root of 3 into A. Root 3 into A. What do you mean by body diagonal? If this is a cube, and a cube has particles at the corners, since they're talking about body diagonal, there should be a particle at the center. There should be a particle at the center. Now, this diagonal, they're asking you, this edge and this, if you remember when we were learning, we would have marked it as AD. This is called as body diagonal. So if at all they ask you for face diagonal, you should remember if this is at the particle at the center of the face, and this will be called as what? Face diagonal. For body diagonal, the distance is square root of 3 into A. Root 3 into A. So root 3 into A, that's what is A? A they've given to be 400 picometers. So on simplification, you will get the answer to be 693 picometers. It's a simple mathematics. Okay, the formula I have to remember, body diagonal, it is root 3A. Find out for face diagonal. Find out for face diagonal and tell me tomorrow what is the relation. So you have to remember this formula. The body diagonal can be determined by the formula square root of 3 into A. A is called as what? Edge length. For this problem, the answer is 693 picometers, because you can see They have given the edge length also in 400 in picometers, and also the options they have given in picometers. Therefore, there is no conversion required. So we can directly substitute and give the answer. The next question. A metal crystallizes with face-centered cubic lattice. The edge length of the unit cell is 408 picometers. The diameter of the metal they're asking the diameter. Now, for a face-centered cubic lattice, how is radius and edge length related? Radius is equal to A by 2 root 2. A by 2 root 2. Very good. A they have given to be 408. So it is 408 divided by 2 root 2. So the simplification, the answer what you will get is 444 picometers. 144 picometers. The answer for this is 144 picometers. Is it right? Can I mark this as an answer?
No, sir.
Yeah, very good. Why I cannot mark this as this is radius?
The 2R.
They're asking you what? Diameter. So diameter will be what? Twice R. 2 into 144. That is 288 picometers. The answer for this question will be option C. The answer for this question is option C. No problem with this? So far?
Yes.
There are a number of questions you can work based on these chapters. I have worked all types of questions, possibly based on the crystal structures. I have done all kind of problems, predicting the structure. I've done calculating the density. I've done calculating the edge length, calculating the radius, all that, or finding out the coordination number. All that we have learned. Different types of problems we have worked. Now it is up to you to solve some other questions. Let us see if possible, if time permits, I will make a set of questions and send it as an assignment. Otherwise, let's see what can be done. But you need to practice. At least these problems you should keep practicing so that you gain confidence to work out similar type of problems when it has been asked in your exam. So the last part of the topic here is called as imperfections in solids. Imperfections in solids. Solids can be imperfect. Though they are called as crystal defects. They are called as crystal defects. Imperfection in solids can be called as crystal defects. There are various crystal defects. We'll have to learn various types of crystal defects. We will go slowly and learn one by one. And it looks huge. The theory looks huge, but you should be in a position to understand that it's very, if you can understand what I'm telling, then it will be easy. All right. Now, any deviation from perfectly ordered arrangement constitute a defect or an imperfection. Now, for an example, if I take sodium chloride, sodium is positive charge, chloride is negative charge. Like this, if I arrange sodium chloride and if I arrange like this, you observe this crystal carefully. It is oppositely charged. It's arranged in order. So we can say this is a perfect crystal because there is no disorderness. Because one sodium, one chlorine, one sodium, one chlorine. It is arranged in order. Assume that one of the chloride ion is missing here. Then it can be called as a defect. Or assume that chloride ion which was there, now that gets into the interstitial position like this. Chloride ion is here now, here. Then it is called as a defect. What is a defect? If an ion or a particle from its lattice position, if it is missing, or it is placed from its original lattice position between the layers, then we call those kind of crystals to be defects, defective crystals, or those can be called as imperfections. Okay. Now I told you, if a crystal is arranged in a regular order, no imperfection. It will be called as a perfect crystal. If an ion is missing from its lattice position, or if ion is replaced from its original position to lattice position to some other place, then those are called as crystal defects. Varieties, many number of crystal defects are there. We will learn these defects, sometimes called as thermodynamic defects. Thermodynamic defects because of heat. because number of these defects depends on temperature. So crystal defects arises basically based on temperature. Therefore, they are also called as thermodynamic defects. Crystal defects are also called as thermodynamic defects. And then the first one is electronic imperfection. First one is electronic imperfection. Generally, electrons are present fully occupied lowest energy states. Electrons are present fully occupied lower energy states. But at high temperature, some of the electrons may occupy higher energy states depending upon the temperature. For example, in the crystal of silicon, pure silicon or germanium, electrons are released thermally from the covalent bond at a temperature above 0 Kelvin. These electrons are free to move in a crystal and are responsible for electrical conductivity. Now, for an example, if you take silicon, silicon belongs to carbon family. It has the covalency 4. 4 covalent bonds are there. This is how you can represent 4 covalent bonds for silicon. This also you can represent. This will be the structure of silicon. This is the purest form of silicon. Now, what they say, if the temperature is increased above 0 Kelvin, the electrons are free to move. What do you mean by that? Now, these bonds are made of 2 electrons. These bonds will break. When bonds are broken, these electrons are free now. This electron starts moving. Therefore, what happens? Electrical conductivity is possible. That is why we call silicon and germanium to be a metalloid. We call them to be what? A metalloid. It has a metal character also, non-metallic character as well as metal character. Therefore, they are called as metalloids. Now, just above 0 Kelvin, the electrons are free to move and therefore responsible for electrical conductivity. This type of conduction is known as intrinsic conduction. Intrinsic conduction means conductivity of a pure substance due to the change in temperature. There is no dopant added. There is no dopant. There is no impurities added. So when you add an impurity or a dopant, then it will be called as extrinsic conduction. We will learn that possibly a little later. Now, the electron diffusion bonds formed by the release of an electron is called as a hole. Now, the bonds break here. Now, assuming that this electron moves here. When this electron moves from this position here to this position, what happens? Here, there is a hole created. This is called as a hole. It's called as a positive hole. In the presence of electric field, the positive holes move in a direction opposite to that of an electron. So in the presence of electric field, what happens is the positive hole moves opposite to the electron and conduct electricity. The electrons and holes in solids give rise to electronic imperfection. So electrons and holes in a solid give rise to what imperfection? Electronic imperfection. Did you understand this? So they have given very clearly in case of electronic imperfection, it happens in metalloids like silicon and germanium. Above the temperatures 0 Kelvin, what happens? The bonds break, the electrons are starting free to move. That is called as intrinsic conduction. But if this silicon is placed in an electric field, electric field will have a positive charge and a negative charge. Now, what happens is this positive holes, when we say positive holes, the charge is not plus here. Remember, the charge is not plus. There's a deficiency in electron here. Therefore, it is called as what? Positive holes. These positive holes move opposite direction to that of electrons and conduct electricity. Like electron moves and conduct electricity, in the presence of electric field, this holes also starts moving, and that also conducts electricity. Due to this, the solid gives rise to electronic imperfection. Is it clear? Simple. Did you understand, students?
Yes, sir.
Yes, sir.
Each and every, there is decrease in strength. Let's see. Anyway, atomic imperfections. These atomic imperfections are also called as point defects. When deviation exists from the regular or periodic, I told you this, when that deviation exists from the regular or orderly arrangement or periodic arrangement around an atom or a group of atoms in a crystalline substance, The defect is called as point defect. Point defect in a crystal may be classified into three. One is called as stoichiometric defect. I told you, if an to the interstitial position, then we call those kind of defects to be crystal defects. More precisely, they are called as what defects? Point defects. So deviation exists from regular or periodic arrangement around an atom or group of atoms in a crystalline substance. The defect is called as point defect. And it can be classified into three. One is stoichiometry. What is stoichiometry? Anybody? What is stoichiometry? Stoichiometry. Now, if I write this reaction, N2 plus H2 giving you 2NH3, is it right? Is it right? Is the reaction balanced? Is the reaction balanced? Is the reaction balanced?
No, sir.
No, it
No,
is not
sir.
balanced. No. If I write like this, can I say now the reaction is balanced?
Yes, sir.
I've written 3. That means 1 mole of nitrogen reacts with 3 moles of hydrogen to give you 2 moles of ammonia. That's the reaction. Now you should remember stoichiometry means the ratio in which the molecules react. That will be called as stoichiometry. So when I didn't write 3, it means this reaction was not in stoichiometry. Are you following what I'm telling? So the ratio in which the reactants react to give product will be called a stoichiometry. Anyways, now stoichiometric defect. Now when I say stoichiometric defect, if in sodium chloride, if I have 10 sodium ion and if I have 10 chloride ion, now tell me, will there be a defect? Is it balanced or not? Is it balanced or not? Number of positive ions is equal to what? Number of negative ions. Is it balanced or not? The ratio is 1:1. Students, please talk to me, students.
Yes, sir.
Now, if I say 10 sodium and 11 chlorine, is this ratio balanced now? Is it 1:1?
No, sir.
No, sir.
No, that means number of negative ion is more here compared to number of positive ion. All right. Now we will learn what is stoichiometric defect. The compound in which the number of positive ion and negative ion are exactly in the ratio indicated by their chemical formulae are called as stoichiometric compounds. Now here NaCl 1:1 ratio stoichiometric compound. Calcium fluoride 1:2 stoichiometric compound, because as the molecular formula says, the ratio is also balanced. Therefore, they are in what? Stoichiometry. The compounds in which the number of positive and negative ions are exactly in the ratio indicated by their chemical formula is called a stoichiometric compound. The defect do not disturb the stoichiometry. The defect do not disturb the stoichiometry. The ratio of number of positive ions and negative ions are called as stoichiometric defect. That means the defect do not disturb the stoichiometry. That means number of positive ions and negative ions will remain same. But there are two types. There are a few types of stoichiometric defects. The first one will be called as interstitial defect. This type of defect is caused due to the presence of ions in a normally vacant interstitial site in the crystal. We will come to this a little later. We will understand this. Generally, we don't talk about interstitial defect. Stoichiometric defect, when we say, we have Schottky defect and Fresnel defect. These two defects are very important. We will come to interstitial defect a little later. It is similar to one of these defects. We will learn. Now, Schottky defect. This type of defect when equal number of cations and anions are missing from their lattice sites, so that electrical neutrality is maintained. This type of defect occurs in highly ionic compounds which have high coordination number and cations and anions of similar size. Anyways, now just observe this. Just observe this. They have given you NaCl. Okay, this is Na. this is Cl, this is Na, this is Cl, this is Na. This is Cl, this is sodium ion, this is chloride ion, sodium ion, chloride ion. This is sodium ion, chloride, sodium, chloride, and this is sodium. Now tell me, there is a perfect order, opposite charges, positive, negative, positive, negative. Anyways, now this is a crystal. Now, as per the Schottky effect, they clearly say equal number of cations and anions are missing from their lattice site. Where I say equal number of cation and anion is missing, maybe I can say one of the cation is missing from here, one of the cation, one of the anion is missing from here. I can say like this. Yes, yes or no? But still, this crystal is electrically neutral because number of positive and negative charge still is what? Equal. But one cation is missing and one anion is missing here. Yes or no?
Yes, sir.
Yes, sir.
Yes,
Now,
sir.
what happens to density? Density is mass by volume. What happens to density? See, one anion and one cation is missing. That means what is decreasing? Mass is what? Decreasing. Volume remains what? Same. See, I've written a box here. The volume remains what? Same. Here was an ion, here was an ion. All right. The volume remains the same, but what's happening? The mass decreases. When mass decreases and volume remains same, what does it mean? Density also what?
Decreases.
Decreases.
In Schottky defect, you should remember density decreases. Why density decreases? Because ions are missing from the lattice points. So highly ionic compounds exhibit Schottky defect, and with high coordination number, like 6, coordination number 6 and 8. Sodium chloride has 6, potassium chloride has 6, cesium chloride has 8 coordination number. So higher coordination number compounds and highly ionic compounds exhibit Schottky defect. In case of Schottky defect, it means the equal number of anions and cations will be missing from the lattice point. Did you understand this?
Yes,
Oh,
sir.
they have mentioned
Yes,
it. Oh, they're in here. All right, now you see here. In Fresnel defect, it's very simple. A plus ion is here. It should have been here. But what happened? Instead of being here, it is moved between the layers here. It's moved between the layers. Expected ion should be here. But what happens? See, this is B minus and it should be A plus here. This also is B minus. But what happens? This A plus is between the 2 layers. Those kind of defects are called as Fresnel defect. This type of defect arises when ion is missing from its lattice site and occupies the interstitial position. The crystal as a whole remains electrically neutral because the number of anion and cation remains the same. Since cations are usually smaller than anions, they occupy the interstitial position. Cations are smaller, therefore they occupy the interstitial position. This type of defect occurs in a compound which has low coordination number, less than 6. 6 and above, it will show Schottky defect. 6 and below coordination number, it will show Fresnel defect. And cation and anion should be of different size. See here, cation and anion should be comparable size, almost similar size. Here, cation and anion should be of different size. Silver is larger, chlorine is small. So these defects are, Fresnel defects are not found in pure alkali metals. So these are alkali metals, potassium, sodium, all these are cesium, all these are alkali metals. So Fresnel defect is not observed in alkali metals or alkali metal halides because cations due to larger size cannot get into interstitial position. So cations in alkali metals are larger. They cannot get into what? Interstitial position. But in case of D block elements like zinc, silver, all these are smaller ions. They can get into interstitial positions. Therefore, they show Fresnel defect. See here, this is an important point to note. AgBr, silver bromide, shows both Schottky defect and also Fresnel defect. Now you tell me, the Schottky defect and Fresnel defect, both are called as stoichiometric defect. Now tell me, what will happen to density in case of Fresnel defect? What will happen to density?
Density remains same, sir.
Very good. Density remains the same. Why density remains the same? Because the
Because ions are
volume
not
remains
missing.
mass. Yeah, ion is in the crystal only. It is in the interstitial position, but it's not in the original lattice position. Therefore, the mass remains the same. So density remains what? Same. Because mass remains same, volume remains same. In case of Schottky defect, density decreases. Remember this. Did you understand these crystal defects? Students, others, Ajay,
Yes, sir.
Yes, sir.
Rupa, Dhanalakshmi, Ritika,
Yes, sir. Understood.
Armugam.
Yes, sir.
All right. Ritika,
Yes, sir.
followed?
Yes, sir.
Very good, very good. Now, next is consequences of Schottky defect and Frenkel defect. What are the consequences? 1 minute. Presence of large number of Schottky defect lowers the density. We learned it already. Frenkel defect alone is, when Frenkel defect alone is present, there is no decrease in density. I taught you now. The closeness of charge brought about the Frenkel defect tends to increase the dielectric constant of the crystal. It's a physics terminology, dielectric constant. Do not worry about this. You can ask what is dielectric constant from a physics teacher, or you can learn from the textbooks. Compounds having such defects conduct electricity to a smaller extent. So consequences, Frenkel defect, density decrease, Schottky defect, density decreases. Frenkel defect, no density decreases, density remains same. And due to these defects, there will be electrical conductance to a smaller extent. When electric field is applied, ions move from its original lattice sites to occupy the hole. It creates a new hole. In this way, holes move from one end to the other. Thus, it conducts electricity across the crystal due to the presence of holes. Stability of the crystal decreases. Stability of the crystal decreases. Now, see here, in case of Schottky defect or Frenkel defect, when electric field is applied, the ions will start moving. If this A plus moves here, what happens? Here, the hole will be created. If this B minus comes here, here the hole will be created. So due to this, what happens? There will be a smaller extent of electrical conduction in both, due to both Frenkel and Schottky defect. Now comes the non-stoichiometric defects. At least we will try to finish off non-stoichiometric defect today. Let's see. Yeah. Let's see how much possible today. Non-stoichiometric defects. Stoichiometry means you know what it is. Non-stoichiometric defect is opposite of that. Now, the defect which disturb the stoichiometry, in case of non-stoichiometry, it will not disturb the stoichiometry defects. Number of positive ions is equal to number of negative ions. Both in Schottky defect and Frenkel defect, if you observe, number of positive ions is equal to what? Number of negative ions. So stoichiometry was not disturbed there. It was maintained. Electrical neutrality was maintained there because of number of positive ions is equal to number of negative ions. But in case of non-stoichiometric defect, the defect which disturb the stoichiometry of the compound are called as non-stoichiometric defect. These defects are either due to the presence of excess metal ions or deficiency of metal ions. So if the metal ions are excess, metal ions are excess or deficient, it will cause non-stoichiometric defects. All right. In case of stoichiometric defects, number of metal ions is equal to number of non-metal ions. Remember that. Now, under that, the first one, what we're going to learn is called as metal excess defect. Metal excess defect due to anion vacancies. Metal excess defect due to anion vacancy. A compound may have metal excess, have excess metal anion, if a metal anion, if a negative ion is absent from its lattice site, leaving a hole. A compound may have excess metal anion, understand this, Metal is always positive charge. Metal cannot have negative charge. All right, metals are always cations. But here they are using a term called as metal anion. When negative anion is absent from its lattice site, leaving a hole. Now that means if you have a positive, negative, like this is negative and this is positive, this is negative and this is positive, this is positive, negative. It's a perfect crystal what I'm drawing. If an anion is missing, then it is called as metal anion. There's a hole left here. Which is occupied by electron to maintain electrical neutrality. This will be occupied by an electron. This empty space or a hole will be occupied by an electron because the crystal should be electrically neutral. Otherwise, it becomes reactive. So this hole is occupied by an electron to maintain electrical neutrality. This type of defect are found in crystals which are likely to possess Schottky defect. Anion vacancy in alkali metal halides are reduced by heating the alkali metal halides crystal in atmosphere of alkali metal vapors. The holes occupies the electrons and they are called as F centers. They are called as color centers. Have you done flame test? In your college? Have you done flame test?
No, sir.
You have not done flame test. Okay. Okay. If I ask you a question, by chance, if you put a small amount of salt in the gas stove, what will be the color of the flame? The color of the flame is blue. But when you put a sprinkle little of salt or something, what will be the color of the flame? You would have observed that. What would be the color? You have not done salt analysis. Acid radical, basic radical, you have not done? Nobody's answering.
Not yet, sir.
Not yet. Okay, anyways. Now, different ions give different color. Sodium gives golden yellow color. Calcium gives brick red color. Barium gives apple green color. Beautiful colors you will get. All these flame tests, this metal ions gives different colors because of something called as F centers or color centers. That is, when an anion is missing a lattice point, electrons will get occupied there. So when you show it to the flame, this electron will have a tendency to move to a higher levels, absorbing energy. Therefore, and when it comes back to its original position, it gives back the complementary color. So this F center, this electron occupying holes are called as F centers. These F centers are responsible for the metals to give different colors. Therefore, otherwise it's called as color centers. So maybe when you start the acid radical, basic radicals, the teachers will show the flame test. You will that time better understand. Next is metal excess defect due to interstitial cation. Metal excess defect due to interstitial cation. See, another way in which metal excess defect. See, here also metal excess defect or not. See, anion is missing. It means one cation is more. That is why it's called as what? Metal excess defect. The other metal excess defect is explained here. Another way in which metal excess defect may occur is if extra positive ion is present in the interstitial site. Extra positive ion. Look at this. This is a perfect crystal, but this is an extra positive ion. If this extra positive ion is present in the interstitial position, then it is called as metal excess defect. All right. Now you can see electrical neutrality is maintained by the presence of an electron in the interstitial site. Electron in the interstitial site. The electron also should be there in the interstitial site. Here they have shown there should be an electron here, interstitial site. This type of defect is exhibited by crystals which are likely to exhibit Fresnel defect. Example, zinc oxide is heated, it loses oxygen reversibly. The excess is accommodated in the interstitial site. So zinc oxide, when you heat it, decomposes to give oxygen. This oxygen is accommodated in the interstitial sites with electrons trapped in the neighborhood. The yellow color and the electrical conductivity of the non-stoichiometric zinc oxide is due to the trapped electrons. See, color is because of the electrons, remember, whether it is the F center or here trapped electrons. Here zinc oxide also shows yellow color. Sodium chloride also shows yellow color. Sodium also shows yellow color. Remember, this is also non-stoichiometric metal excess defect. This is the representation. Metal excess defect due to extra cation. Here, metal excess defect due to an anion vacancy. Anion vacancy, you get in that place electron occupied. Consequences of metal excess defect. Right. Consequences of metal excess. The crystal with metal excess defect are generally colored due to the presence of free electron. I told you, F center and others also I told you. See, you should remember the consequences. Why are we learning? Because it gives some property change. That is why we are learning these defects in the chapter. The crystal with metal excess defect conduct electricity due to the presence of free electrons and are semiconductors. All metal excess defect crystals are semiconductors because they conduct electricity due to the presence of free electrons. As electric transport is mainly by excess electron, these are also called as N-type semiconductor or negative type semiconductors. Because electrons are excess, therefore they are called as N-type semiconductors or they are called as negative type semiconductors. Crystals with metal excess defect are generally paramagnetic. Crystals with metal excess defects are generally paramagnetic. Paramagnetic means they will have unpaired electrons. They will have unpaired electrons. They will be attracted towards the magnetic field. Attracted towards the magnetic field. That's why it's called as paramagnetic. We will learn the magnetic properties of the crystals in the next class, that is tomorrow. Due to the here only the answer is given due to the presence of unpaired electrons at the lattice sites. When crystal is irradiated with white light, the trapped electron absorbs some component of white light for excitation from ground state to the excited state, and this gives rise to color. Such points are called as F centers. I taught you this. Farbe, F means Farbe, which means color in German. Such excess ions are accompanied by positive ion vacancy. These vacancies serve to trap holes in the same way. You don't worry, same way as an anion vacancy trapped electrons. The color center thus produced are called as V center. Electrons occupying this empty space is called as F center. Here, if the excess ions are accompanied by positive ion, these vacancies serve trap as a hole in the same way as an anion vacancy trapped electrons. So if positive holes are there, they are called as V centers. Again, they also gives color. So excess electrons will give you F centers, excess holes give you V center. Both are responsible for colors of the crystal. Metal deficiency defect by cation vacancy. Metal deficiency defect by cation vacancy. In this, a cation is missing from its lattice site. To maintain electrical neutrality, one of the nearest metal ion acquire two positive charge. This type of defect occurs in compounds with metal, which can exhibit variable valencies, like transition metal, nickel oxide, iron oxide, etc. See, D block elements will show different valencies. Now here you observe, here it should be A plus, and here it should be A plus. Then it is what? Neutral. But now this A plus is missing. When A plus is missing, to maintain the neutrality, electron neutrality, you can see here it is A2 plus. They have written A2 plus, metal having higher charge. Now D block elements, generally they can show variable oxidation state. You would have heard of iron, Fe2 plus, you would have iron Fe3 plus, ferrous, ferric, all that you would have learned. Likewise, all the D block elements will show variable oxidation state. We will learn the property in the D block elements chapter later. All right, those are called as what? Metal deficiency defect by cation vacancy. Whenever a cation is missing, the neighboring cation will acquire higher charge. It is A plus here it is A2 plus. Did you understand this?
Yes, sir.
Okay.
Yes, sir.
Now, last paragraph, we will learn this and we'll stop. Possibly we'll continue the class tomorrow. By having extra anion occupying interstitial site, in this, an extra anion is present in the interstitial position. The extra negative charge is balanced by one positive charge in the adjacent metal ion. Such anions are usually larger. It could not occupy the interstitial site. Thus, the structure has only theoretical possibility. No example so far. No example so far. What it says, if extra anion is present, then the adjacent neighboring ion cation will have one extra positive charge. But they say this is theoretical possibility. There is no example known so far. All right. We will learn, okay, we'll learn this and properties of solids we will learn later. Consequence of metal deficiency defect. Due to the movement of electrons, an ion A plus changes to A2 plus. Thus, the movement of electron from A plus ion to an apparent of positive hole and the substance are called as p-type semiconductor. See, A plus from here, the charge changes to A2 plus. That means creates a hole. Therefore, it's called as positive type semiconductor. Impurity defect. These defects arise when foreign atoms are present at the lattice sites in place of host atoms or a vacant interstitial site. In former case, we get substitutional solid solution, while in the later case, we get interstitial solid solution. Solid solution, we will learn. Next chapter, we will learn solution, different types of solutions, all that. Now, if there is a foreign atom present in the original lattice site, they are called as impurity defect. That's all you remember. The formation of former depends upon the electronic structure of the impurity, while that of later on the size of the impurity. Don't worry about this. Impurity defect means from the original lattice position, if I have NaCl crystal, instead of Na plus and Cl minus, if any other ion is present, then it is called as impurity. If it is zinc is present or even potassium is present, any other is present, then it is called as impurity defect. You can clarify any doubts with so far what we have done. We have done a lot of theory today with few problems. So if you have any clarification, you can ask me. Students, if you have any clarifications, you can ask me.
No, sir, no doubt, sir.
No doubts. So in the exam, you should practice all this. Keep repeatedly watching these. Whenever you have free time, watch these videos from all the subjects so that you will get more confidence. So it will be like a preparation.
Yes, sir.
Class, ma'am. Ninth class.
Sir, you are not audible, sir. Children, has he completed the class?
Yes, ma'am.
Okay, dear. Okay, dear.